Hello everyone. A lot of people have been asking me to explain one of the great unsolved problems in mathematics. It's called the Riemann Hypothesis. Now the fact that a lot of people have been asking me to explain this tells me two things. First, my life is weird, and two, that you're a bunch of mercenaries, because you've probably heard that the Riemann Hypothesis is one of those $1 million problems, that if you solve it, you will win $1 million. Now it is one of the great unsolved problems in mathematics. It was number 8 on David Hilbert's list of challenges to 20th century mathematicians. It was number 1 on a similar list of challenges to 21st century mathematicians, and it is one of these Clay Institute $1 million prize problems. If you've heard of it at all, you may have heard that it's something to do with prime numbers, but you don't know exactly what. So I'm going to attempt to explain it to you. Although it's not going to be easy. They don't give away $1 million prizes for school maths. But if you want it, the too long did not watch version is the prime number theorem. The prime number theorem approximates how many primes there are less than a given value x. Now it is an approximation, it's not the true value. There is going to be a difference from the true value, an error. Now the Riemann hypothesis will tell you how big that error term is. If you want a little bit more information, the error term that we're looking for is related to a function called the Riemann Zeta-Function, and particularly when that function is equal to 0. So the Riemann hypothesis is the zeros of the Riemann Zeta-Function all lie on the line a half plus it. So these are complex numbers, but with real part equal to a half. Now, to explain this hypothesis, I'm going to go into the prime number theorem in a little bit more detail. I'm going to tell you what the Riemann zeta function is, how it's related to primes, why the zeros are important, and if I have time, I will prove that black equals white and cat equals dog. So let's start with the prime number theorem. The prime number theorem was first thought of by Gauss at the end of the 18th century when he was only 15 years old. You'd think he'd be busy texting and hanging around the outside of shops, but no, he's busy doing the prime number theorem. Now, if we call the number of primes less than x, if we call that pi of x, then the prime number theorem says that pi of x divided by x over log x tends to 1 as x tends to infinity. So some people say that pi of x twiddles x over log x. You can think of that as pi of x, the prime counting function, is approximately x over log x. So we do an example of that. If we say x is 100, then the number of primes less than 100. There are 25 of them. But our approximation, x over log x, gives you 22, which is not bad really for an approximation. In fact, the error gets proportionally smaller the larger the numbers are. So if I use x as 1 billion, then the number of primes less than 1 billion is something like 50 million. And our approximation, x over log x, gives me 48 million. It's about 2.5 million off from the true answer. But proportionally, it's a smaller error. 40 years later, Dirichlet and Gauss came up with an even better approximation for pi of x. They said that pi of x twiddles this integral between 2 and x of 1 over log t dt. It's called the logarithmic integral, and it is an even better approximation. So for example, if I had x was 1 billion again, then the logarithmic integral actually gives me an approximation of about 50 million. It's in fact only 1,700 away from the true value, so it's a really good approximation for pi of x. Now there is another quantity which I'll mention now because it's going to turn up later. We've seen pi of x, which is the prime counting function. You get 1 point for each prime. I'm going to introduce now something called j of x, which is the prime power counting function. Again, you get 1 point for each prime, but you also get half a point for each prime squared. So something like 9, which is 3 squared, you get half a point. You get 1/3 of a point if it's a prime cubed. So 27 scores 1/3 of a point because it's 3 cubed. And you get, for the nth power of a prime, you get 1 over n points. So that's the prime power counting function. Remember that, because that is going to turn up later. You can see it's related to pi using this formula, and you can reverse that. You can actually get pi from j using this other formula, which has some more minuses and pluses in it. But the prime number theorem was actually only proved 100 years after Gauss thought of it, and it was finally proved using the Riemann Zeta-Function. The Riemann Zeta-Function was actually based on something Euler was doing in the 18th century. You see, Euler, he was interested in infinite sums like 1 plus a half plus a cube plus a quarter, and that goes on forever. If you've seen that before, you may know that's called the harmonic series, and it is tending to infinity. Very slowly, it's tending off to infinity. What Euler was interested in were powers of those fractions. So 1 plus a half squared, plus a cubed squared, plus a quarter squared, and that going off to infinity. And he found that that doesn't tend to infinity, that actually tends to a number. The number is actually pi squared over 6. So if that's the first time you've seen that, hey, surprise pi. If you do it for cube powers, 1 plus a half cubed plus a third cubed, that actually tends to 1.202. If you do it for fourth powers, you get pi to the 4 over 90 and so on. So you actually get proper values, except for when the power is 1, the harmonic series. That tends off to infinity. In general, Euler was studying these sums of 1 over n to the power s. Now what he found was that this infinite sum was equal to an infinite product of primes. If p is your prime, then it's a product of p to the s over p to the s minus 1. So you go through the primes like 2 to the s over 2 to the s minus 1, multiply that by 3 to the s over 3 to the s minus 1, multiply that by the next prime, 5 to the s over 5 to the s minus 1, and that goes on forever too. Now what he showed was, if say s is equal to 2 then that infinite product of primes is equal to pi squared over 6. Or if s was equal to 1, then that infinite product of primes goes off to infinity, like the harmonic series goes off to infinity. Which is actually a proof that there are infinitely many primes. Because if there were only finitely many primes, you'd get a finite number. Now it's the Euler function that Riemann decided to rip off. Study. Bernhard Riemann was apparently a shy and timid individual, but mathematically very talented. Gauss was actually his lecturer at university. It was Gauss who persuaded Riemann to swap his course from theology to maths, and in the end Riemann ends up running the place. He becomes head of department in the end. It was in 1859 though that Riemann wrote his paper on the zeta function. Now it's one of the most important papers in number theory. It's only 10 pages long. Riemann never wrote on number theory before or since that paper. This was his one and only time, and it just turns out to be one of the most important papers in number theory ever. It's like the mathematical equivalent of a mic drop. Peace out, I'm done. Riemann's zeta function was basically Euler's function, except he used it for all complex numbers. So s could be any complex number, not just 1 and 2 and 3 and 4. The problem with that is it's only defined when the real part of s is greater than 1. Otherwise it explodes, it goes off to infinity like the harmonic series. What Riemann needs is a function that's defined for all complex numbers, but is equal to the Euler function when the real part is greater than 1. Now, the amazing thing about complex analysis is there is a way to do that, and there is only one way to do it. So if you think about it, what it means is, if you know a value of a function for some complex numbers, you automatically know it for all complex numbers, which is like, what Riemann did is he considered this infinite sum. It's like the Euler function, but you've got alternating plus and minus signs in it. And he divided that by this factor, 1 minus 2 to the power 1 minus s. And this function is defined for complex numbers where the real part of s is greater than 0. And it's equal to the Euler function when the real part of s is greater than 1. This is the function we're looking for. Now this defines a value when the real part of s is positive. What about when the real part of s is negative? To do that, what Riemann did next was he considered that strip between 0 and 1. And in that strip we have this true identity for the zeta function. It's not very nice to look at, I know. So you've got the zeta of s equals some junk. And it's got sine in there, and it's gamma and pi. It's a lot of junk. Multiplied by zeta 1 minus s. What this means is the values are kind of reflected in the real part of s equals a half line. They're reflected and then multiplied by that horrible factor. So that means we can reflect all our positive values into our negative values, and that will define it. So if you want to know zeta of minus 1, then you would multiply it by that horrible factor with s equals minus 1, which is only minus 1 over 2 pi squared. Then you would times that by zeta of 2. Now we know the value of zeta for 2. If you remember that from before, that was pi squared over 6. So altogether, zeta of minus 1 is minus 1/12. Now, if we consider the zeta function as an extension of the Euler function, then some people consider the sum 1 plus 2 plus 3 plus 4 going on forever. Some people consider that to be equal to minus 1/12. And in a way, it kind of is. So to recap, the Riemann zeta function comes in 3 parts. When the real part of s is greater than 1, then it's just equal to the Euler function, which you can write as a product of primes as well. When the real part of s is between 0 and 1, then it's equal to this alternating sum. And when the real part of s is negative, well, you take the positive values, reflect it in the real part of s equals a half line, multiplied by a horrible factor. And that defines it all. Anything I haven't defined, you can define by taking limits. So zeta of 0 is equal to minus a half. Zeta of 1 tends off to infinity, just like the harmonic series did. The next question is, when is this function equal to 0? Well, for a start, we know that when the real part of s is greater than 1, it's never equal to 0, because it's a product of primes, and none of those factors are 0. So what about the third case, when it's negative? Well, in the third case, you might be able to see some zeros at minus 2, minus 4, minus 6, and so on, because we've got a sine function in there, and that's when the sine function is 0. Those zeros are called trivial zeros. Otherwise, we've got non-trivial zeros, and they exist in the strip between 0 and 1. And they're also symmetric around the real part of s equals a half line. So Riemann wondered if his zeta function could be written in terms of the non-trivial zeros. This is like what you do with a polynomial. So imagine you have a polynomial like x cubed plus 2x squared minus 13x plus 10. Well, you know you can factorise that into 3 factors because it's a cube, and you find the factors by looking for when the polynomial is equal to 0. For example, if x equals 1, then the polynomial equals 0. So x minus 1 is a factor. If you do that again, if x equals 2, the polynomial is equal to 0, so x minus 2 is a factor. And if x equals minus 5, the polynomial is 0, so you can say x plus 5 is a factor. And that's how you factorise a polynomial. So Riemann wondered if you could do something like that with the zeta function, and you can. So he worked out that the zeta was equal to, again, some junk. You've got gammas still in there and pi still in there, multiplied by a product of factors involving the non-trivial zeros. That's 1 minus s over rho. Rho are your non-trivial zeros, so you can do that. So on one hand, you've got zeta, which is your normal zeta function, which was defined with its 3 parts. On the other hand, you've got zeta written as a product of its non-trivial zeros, and those two things are equal. So you do, you equate them and then you just mess around with it. You take logs of both sides, you do some calculus, some complex analysis, some theorems of residues. It's all very nasty stuff, I'm not going to do it now. But in the end you end up with a result involving j of x. That's the prime power counting function, if you remember. And that is equal to the logarithmic integral of x, you may remember that from the prime number theorem, plus a sum of logarithmic integrals of x to the power rho. Rho are your non-trivial zeros, so they're still there. Minus log of 2, that's just a constant, that's still there because there was a factor of a half and that's still there. Your pi's have disappeared, they've cancelled out and disappeared. And your gamma has turned into this integral, which is not very nice looking and also not very important, don't worry about it. So we have a kind of a prime number theorem now for j of x, the prime power counting function. We can now say j of x twiddles the logarithmic integral. And we have an expression for the error, the difference. If we subtract j of x minus the logarithmic integral is equal to this error term. The most important term in the error term is that sum of logarithmic integrals of x to the rho. If rho are your non-trivial zeros, they are really controlling the size of that error term. Now your non-trivial zeros are symmetric around the real part of s equals a half line. If all your non-trivial zeros actually lie on the real part of s equals a half line, then that error term will be as small as possible. Nearly 40 years after Riemann and 100 years after Gauss first thought of a prime number theorem, mathematicians were finally able to prove it. And the proof involved the Riemann Zeta-Function. In particular, they showed that the zeta function has no zeros on the line real part of s equals 1. And that did it. That proved the prime number theorem. Hooray! Now the error term for the prime number theorem, well, that's controlled by the non-trivial zeros of the zeta function, the Riemann hypothesis, and that still isn't proven, so boo. But if the Riemann hypothesis is true, then the error term has a bound. It has to be less than c square root of x log of x for some constant c. So it can't be as big as it wants to be. The prime number theorem also tells us that the average gap between consecutive primes should be about log x. And if the Riemann hypothesis is true, then there is a similar bound on consecutive primes. Other consequences of the Riemann hypothesis are things like the weak-Goldbach conjecture. The weak-Goldbach conjecture says that any odd integer greater than 5 can be written as the sum of 3 primes, and that would be true if the Riemann hypothesis is true. Another consequence, one I like, is if the Riemann hypothesis is true, then there will always be a prime between consecutive cubes. Now the reason I like that is that means you can define a constant theta such that theta to the power 3 to the n will always generate a prime number for all the values of n. It's called a Mills constant. They already exist actually, but you have to use x as a prime. Now if Riemann hypothesis is true, then x doesn't just have to be a prime. And then you would get lots more Mill constants, the smallest of which would be 1.30637 something something. So I like that one. There's a lot of evidence for the Riemann hypothesis. We found lots of zeros, trillions of zeros on that critical line, that real part of s equals a half line. Unfortunately, Godfrey Hardy showed that there are infinitely many zeros on that line. So this is evidence, but none of it is conclusive evidence, I'm afraid. Now, if you want to win that $1 million, you have to prove the Riemann hypothesis. Unfortunately, if you find a counterexample, if you find an example of a zero which is not on the critical line, the real part of s equals half line, and you disprove the Riemann hypothesis, no $1 million. No $1 million for you. No, there is no $1 million if you disprove it by counterexample. So I'm afraid, mathematicians, it is now over to you. And if you have been, thanks for watching.